Okay, I hope now everyone is able to hear me properly. And if someone is not able to hear me properly, it's probably on your end. It's not on my end. Okay. In weekly, they said 7 to 9 class. I don't know because they informed me 5 to 7. So it's probably on Blackbucks side. And probably if these many people have joined, that means that you guys were notified that this class will be held on 5 to 7. Hence, it's completely fine. Uh, for whoever Kalki is more important, they can enjoy Kalki. We'll continue with our class. We are already, I waited more than 5 minutes now. If after this someone asks me what is the topic, sir, you can tell that how we actually decompose fruits. Okay, that's the topic, decomposition of fruits. Okay, guys, my screen is visible. My screen is visible. Yes, no, yes, no. Okay. So last time we discussed about regression model, and this is how we picked up some model, okay, what we'll do and so on and so forth. Okay. I asked you guys to practice with heart disease data set that you already have. If you haven't done it, it's fine. Ideally, you should have done it. Okay. Now we will see how we can pick up a model, okay, based on based on um, this classification. So for regression, we saw. Now for classification, how we can choose it. Let's try to see it. Okay, give me just 1 minute so that I can actually get you that image. Okay. Bang, bang. So this is a markdown field, and this is how we are importing image. Type this, and then okay, why am I not getting it? Why am I not getting it? Why am I not getting it? Yeah, I should get it right. Oh, .png, missing .png. Okay, so you already know, guys, whoever is asking topic name, you guys can answer them. Okay, you already know in the last class, we saw how to choose model for a regression. Okay, and you already have seen heart disease data set a lot. Okay, we have 303 sort of rows in this heart disease. We will choose a model. So for example, we start, okay, we'll start, and then we know that we have more than 50 samples, 3 samples, and then we know that we have different categories, basically target if someone has heart disease or do not have heart disease, and so on and so forth. So we do have a category. We are not basically trying to calculate some sort of quantity. Is the data labeled? Yes, it is labeled, right? It is labeled. The data is labeled. Then, do we have less than 100K sample? Yes, it's just 303, so it is less than 100K sample. Then, what do we get? Linear SVC. This is something that we can use. So how we'll do? First of all, okay, linear SVC. What does linear SVC stands for? It stands for linear support vector classifier. Okay, it stands for linear support vector classifier. Now, Let's try to use this LVC and see what we are getting. Okay. Following really same steps up until now that we have been following, trying to get heart disease data set, splitting into features and then test data, and then basically trying to calculate heart disease. We have already loaded this heart disease data set, and hence why I'm just directly doing it. Okay. Same thing, fitting the model. But the only thing is now we are using linear SVC. Iteration, basically 1000 iteration. This is what we are doing. Okay, 1000 is technically default. Dual auto, which means it chooses best parameters for the model automatically. And what we are getting an accuracy score of 0.86. Okay, straight out of the box with no tuning or improvements, our model achieves 85% accuracy score. Also, this is, I mean, although this is like really good result. Okay, but what if we want to get a better result? We think we can get a better result in here. Then what can we do? Not working. Okay. If we are saying it is not working, do we have a text data? No, we don't have a text data. Okay. What else can we get? What else can we choose? Okay. What we can do is, okay, if we don't want to use KNN classifier, we can technically use ensemble classifiers. Okay, we can use ensemble methods. Remember, we were also using ensemble methods for what? We were using ensemble method for our regression problem. In the same way, we can use ensemble problem here. Okay. Assume we want to have much better accuracy given the sample size. We can in here use ensemble classifier. Okay. Okay then. How do we use ensemble classifier? From sklearn.ensemble import random forest classifier. Right, this is what we need to do. And then we say we do the same thing. Feature split, label split, using random forest classifier, using estimators. By default, we are using 100. Obviously, this can be changed, okay, for better accuracy and so on and so forth. And right out of the box, we are getting what? 85% of accuracy score. Last time we saw that on 200, we were getting better results. So we'll just set it to 200. 100 is default, right? And we are also getting here 86%. It's like somewhat same sort of accuracy score that we are getting. Okay, default parameter is not performing as well as we want. If you want, you can experiment more, going like up until 1000. We have seen this already. Okay. If you would like to learn now, if you would like to learn more about random forest classifier, or if you want to learn more about how does random forest work, you can go on Wikipedia, learn more about it. The explanation is already given there. There are so many resources which explain this in much more detail. In this course, we will not cover. Okay. Some things that you need to keep in mind. Okay. We can cover a lot of models, but it is not possible to cover in this course. So there are few guidelines that you just need to keep in mind. Okay. If you have structured data, which is, for example, tables, spreadsheets, or data frame, you usually use ensemble methods such as random forest. Okay. That's just one of the models that is available in scikit-learn. There are so many other models that are available, but we can't cover all of that. It's highly impossible given the time frame that we have. Okay. It's also not so practical. Okay. Okay. It's not so practical. Now, what about other models? Sorry. What about if you have unstructured data? So if you have unstructured data like text, images, audio, and some sort of blob sort of data like that, you ideally use deep learning, okay, or you use transfer learning, okay. For that, mo most common library that we use is either TensorFlow or PyTorch, okay. We'll try to look into it deep learning, how we do it later in this course, okay. For now, you just need to understand this, okay. You choose the model, then you basically fit the model to the data and then make this prediction. Again, we have been seeing this a lot, okay. In scikit-learn, the process is straightforward. We just use this fit function, which is provided to us. That's it. What is X? X basically include data, feature variables, features. Okay. What is Y? Y is basically labels and target variables. Okay. We have seen all of this. Cool. What else? What else? Now, like I keep on saying, if I start explaining each model in detail, basically it will be like 600 or 700 pages of whole course book, which is impossible, right, to cover. And that is why it is essential that you guys read any model that you want to have deep understanding of. You can just read it on yourself. I am covering the very basic and high level understanding of how you can do things and what you need to do. And these are the important things that you need to keep in mind. It is very repeatable process that we have done up until now, and this is what you need to know. Okay. How do you make predictions? Simply, you do predict. Okay. How? For example, like this. This is how you make predictions. Okay. Given data X, which is whatever that can be data, you can even pass on single row. Okay. You can have a prediction and prediction is always based on your target label. So our target label consists of what? 0 and 1 in heart disease data set. 0 means someone does not have a heart disease. 1 means someone has a heart disease. That is what it is. Okay. That is what it is. Cool. We have seen all of this. What else can we get? We can get some sort of accuracy score, obviously, to get the metrics. So this is what the accuracy score is here. At least in here, this is what the accuracy score is, 0.47. Okay. Oh, this is not correct actually, because this YPRED is coming from uh, previous test that we did. Okay. Now let's see. Okay. So the accuracy score is 0.86 or something. Okay. Now there are two methods to get accuracy score. One is obviously with NP mean, compare Y prediction with Y test, and then we get accuracy score, or we can just use this function which is given by scikit-learn out of the box. Okay. Then we can also get probabilities, okay, of the classification level, okay, which is basically we are getting probability of the prediction using predict proba. Proba is nothing but probability. Okay, it is just short form. Okay, or we can get directly prediction, right? Like this. Cool. Um, what does probability here means? What does probability here means? In here, the output means the model is predicting label 0, which is at index 0, with a probability score of almost 0.88. Okay. The highest probability at score at index 0. Okay. And it can be over 0.5. Okay. Now, where does 0.5 comes from? When I'm saying like um, it should be over 0.5, where does this 0.5 comes from? 0.5 comes from the fact that heart disease data set, okay, heart disease data set is a binary classification, right? 0 and 1, that is what we are predicting. Hence, the probability should be at least over 0.5. Okay, that is where it comes from. Okay, now in our housing data set, okay, in our housing data set, okay, we can use predict as well. This was our housing data set that we were working with, comes from scikit-learn itself. Okay, and there are few ways to do it. Mean absolute error, this is how we can do, and we get somewhat around 0.32. Okay, now we know what predict does, we know what predict probability does, and we also know what fit does. Okay, to make any sort of predictions, we use predict or predict probability. Okay, and to find patterns in the data, we use fit. Okay, we have covered almost all of these. I'm just repeating so that everything gets into your brain and you understand what we are doing. Okay, if we bring down the code, okay, from like basically previous classification model, okay, we can say see that like we try to calculate a score a lot. Okay, and in which cases a score is basically good. Okay, so we can call score method and evaluate our test data. Definitely, where is the score really viable? So usually when we are doing some sort of classifier sort of thing or regression sort of thing, we can use a score and get score. Okay, behind the scenes, what score does is it makes predictions using the X-test data, okay, using our trained model, and then compares those prediction to the actual labels. Hence, what we get score from. Okay, as a classification model which predicts 100% correct would receive an accuracy score of 1.0, which is 100%. Okay, our model does not get 100% accuracy score in here. It somewhat get what, 86%. Okay, let me do it again so that we know it. So we get somewhat 85% of accuracy score in here, right? Okay, how do we evaluate on scoring? We have 1 minute. We can also use custom scoring. Okay, how do we do that? We basically do cross-validation score or grid search CSV. This is also we have used. Okay, so let's see it again. This is our heart disease model, correct? And we get a score as such. 85%. And then we can get a cross-validation score. Okay, which we have imported here from scikit-learn. Right? And what we get, we see, okay, 0.81, 0.86, 0.78. What's happening here? The first difference that you will see that it returns an array, okay, instead of only single number. What is cross-validation doing? Cross-validation basically splits into 5 sort of different grids and tests our model with 5 different sort of data sets. That is what it is doing. Okay, that is what it is doing. Okay. Let me give this also to you. This is what is happening. Okay, this is what is happening. We have a normal test data split. This is what we are doing normally, usually. We have, for example, 100 patient, then we do 80-20 sort of split, right? This is what we normally do. With cross-validation score, what happens that we do 80-20 split for the first grade, but then we always take different sort of sample size. You see, we are basically rotating. We are basically rotating. Okay. Why do we need to do this cross-validation? Why do we do that? The reason for this is obvious. We need to test that how our model actually behaves when we provide a different sort of data set and training model. And which is the most optimal training model and data set that we should provide to get the most optimum result. That is why we do cross-validation. Why always we do 5-fold? Okay. Why we do the 5-fold? The actual name of this setup is basically K4, okay, where K is technically an arbitrary number that we can change. And that is where you see CV, and this can be changed. 5 is just basically a default. If we want, we can split our data even into 1000 and rotate. Okay. Ideally, you want to do something really fast. That is why we split it into 5. But you can even do it in like 500 if you if time permits. Okay. Now, we have CLF score, we scoring cross validation score. Okay. We haven't used scoring at all. Okay. Scoring is basically none by default. Okay. So there is a third parameter that a cross validation actually takes, which is scoring. Scoring is basically none by default. Now, if you notice, okay, different scores each time you call cross validation score. This is because each data split is random every time, right? Now, why is the scoring set to none by default? Is it basically uses the same metric as score for whatever model we pass. Okay. In this case, our model CLF basically, which is an instance of random forest classifier, which uses mean accuracy as default score metric. Okay. You can change the evaluation score, okay, and basically you can make it so that it uses different scoring parameter. You can refer to scikit-learn's documentation how you can do it. Okay. Now, there are four main classification metrics that you really need to be concerned about. There are four main classification metrics that you really need to be concerned about. Okay. Accuracy, area under ROC curve, okay, confusion metrics, and classification report. Up until now, we have seen accuracy, confusion metrics, classification report, but we haven't seen enter ROC. We'll do this in coming soon now. Okay, so for our heart disease model, obviously we have seen the score. Cool. Accuracy is the default metric for the score function within basically scikit-learn. Okay, and ideally, usually scikit-learn always returns it in decimal format, but if you want in percentage format, you can easily convert it as so. Okay, just normal Python script, get the score, multiply it with 100, you can get percentage. And I am saying here, get me only 2 decimal points. Now, what is area under receiver operating characteristic or ROC curve? Okay. It's a very huge name. It's a very huge name. For example, this. Okay. Area under receiver operating characteristic or ROC curve. It's usually referred to as AUC, area under curve. Okay. And the curve they are talking about is receiver operating characteristic for short. Okay. Now, if here someone is talking about AUC or ROC, they are probably talking about these things. So ROC curves basically are comparison of true positive rate versus false positive rate. ROC curves are basically comparison of true positive rate and false positive rate. Okay, we have already seen what is true positive, false positive, true negative, but again, I'll just write it down here because I've done this several times. Still, you guys are sometimes confused. Okay. So it gives you the rate. ROC curve gives you a comparison between rate of true positive versus false positive. Okay. Now, since we know this, let's start computing ROC curve. Okay, for our heart disease data set. How can we do it? We import it from metrics from scikit-learn ROC curve. Okay. We do this prediction, predict proba, make prediction with probability using X test. Okay. Again, maybe let's just take probabilities of positive classes only, where like we have ones. Okay. And then we will start calculating FPR, TPR, and threshold. Okay. Let's see what we get as false positive rate. Okay. And what we use ROC curve function to get these values. Oh. Now, if you look at these on their own, it doesn't make any sense. Basically, ideally, you need to see it visually to make sense out of this whole data point. Otherwise, a bunch of decimals makes no sense, right? Okay. How can we do this? Definitely what we'll do is use matplotlib. So we use matplotlib, we try to use pyplot, which is what? Which is the default interface. Okay. We use default interface to do quick plotting. We create a function to plot it. We pass in FPR, TPR, right? We are plotting an ROC curve, okay, between false positive rate and true positive rate. Then what we are doing in here, we are basically plotting ROC curve. We say the color is orange, label is ROC. What are the two things? FPR, TPR. Again, we basically plot a line with no predictive power. Okay. Again, plotting is between 0, 1, and so on and so forth. We give color dark blue, line style is this. Okay. X label false positive rate, Y label true positive rate, title, and then we also want to see legend. Legend is what? Site indicator, which tells what is what, and then we can show. And let's see what we get. This is basically the legend. This is what guessing is. This is ROC. Okay. ROC is what? Okay. Let's see. Let's try to understand again. We are getting guessing. Guessing is between 0 and 1, 1 and 2. It is basically a mean median line that is coming here. Okay. And then this graph, which you see, this orange one, this comes from our FPR and TPR, true positive rate and false positive rate. Okay. Now, looking at this plot for the first time, it might still be confusing. The main thing to take away here is our model is doing far better than guessing. What does this mean? Guessing is must more like 50% sort of thing, okay? While our model is trying to, is more leaning towards true positive rate rather than false positive rate. Hence why it is much better. Okay? If you see this graph, it is leaning towards more true positive rate rather than false positive rate. Okay? Okay. Let me again write this here. Okay. Now, scikit-learn implements a function to calculate this, which is obviously ROC AUC score. Okay. And the maximum ROC AUC score you can achieve is 1.0. Okay. Or closer to 1.0. So let's see what sort of score are we getting. So we can get it from matrix ROC AUC score. And let's try to get it again, passing Y test and Y probability that we calculated up in here. Okay, Y probs. Okay, and let's see what we get. And we get 0.93. Okay. Now, although it is a good practice to plot, technically, we didn't need to create plot ROC curve. Technically. Okay. Because scikit-learn also allows us to plot ROC curve directly from estimator model, which we have already seen much earlier. Okay, and how we can do it? How we can do it? We can directly plot it from ROC because from scikit-learn, because scikit-learn in itself also has matplotlib inside within their library implemented for such cases. And look here, it generates roughly a similar sort of graph, and it also gives us direct what? AUC ROC score 0.93. Okay. The most ideal position for ROC curve is to run along the top left corner of the plot. What is the top left corner? This is the top left corner of the plot. Okay. This means that model predicts only true positives and no false positive, and would result in ROC AUC score of 1.0. Okay. Which is technically not possible because there will always be some sort of error rate, and this is fine. Okay. And how can we, okay, for example, if we pass y test and y test again to ROC, then you see that we get exactly this graph. And if you see, this is very similar to this. This is technically not good because this means that we are just using redundant data. Okay. Ideally, we should have some form of error rate at least. Okay. Hence, it is unlikely that we will get this. Okay. Now we know what is ROC score. We have already seen confusion metrics. Confusion metrics is just a quick way to compare the labels and basically get, okay, how it predicts, get true positive, false positives, and so on and so forth. Now, if you remember, okay, true positive, true negative, false negative, and so on and so forth. This is what we get. Right. Now, this is not easily visualized. We can actually visualize confusion metrics in a much better way, and we can do this by cross tab like this. So when it is 0, 0 is correct, when 1, 1 is correct, okay? And if it is getting 0, 1, it's false. If it is getting 1, 0, it's false. Okay? XOR basically. How else? How else? We can create a confusion matrix also using scikit-learn, right? We have been using pandas, but we can also do it with scikit-learn directly. How? We can directly display it, okay? And it will take something like this. There. We had 303 data points, and if you see, green, yellow is more sort of on the good side, and like purple is on the bad side, and so on and so forth. True label, predicted label. Okay. So you can visualize it. Okay. Scikit-learn has much more different implementation for this. Actually, you can go and see for this on like how you can get this. This one is from estimation, and then there is another one which we can do from prediction. So this is what we can get from prediction. Okay. Now again, classification report we have seen, but again, let's see it. Classification report. I already defined it earlier. how the classification report works, and so on and so forth. This is also mentioned in scikit-learn's classification report. Okay. Let me give you much more detailed definition on each of these, what it does. Okay. So precision, recall, F1 score, support, accuracy, macro average. This is what we are not doing. It is basically short for macro average, gives you average precision. Okay. Weighted average, I've talked about it. Weighted means, I've also talked about it. Okay. Okay. We don't need this is you can read about it, what it is. Okay. Now, when should you use it? It can be tempting to base a classification models performance based only on accuracy, and it is a good metrics, except when you have imbalanced classes. Then you should look into some other metrics as well. Okay. Okay. For example, let's say there are 10,000 people and one of them had a disease. You're asked to build a model to predict who has it. You build a model, you find your model to be 99.99% accurate, which is good, right? But the problem is your model, your data set is so imbalanced because you can't make the right prediction because you only had one false negative. That is why it is not good. Okay. Hence, in this case, you should also look into F1 score. Right. Okay. Now, for example, let's get a data frame for classification report and boom. Okay. Same examples that I talked about here. Okay. If disease true is 10,000, okay, and disease true, let's just say only one person has disease. Okay. And now, if you see here, we have accuracy of what? 0.99, which is almost 99%. Okay. But is it useful? No, it is not useful. Why? Okay. Because if you look at macro average, if you look at macros, F1 score, and so on and so forth, you will understand that this is actually imbalanced. Okay. Hence, recall, recall becomes very much important. Precision and recall become very much important. Okay. If you see the precision here, you see precision here in this table. What are we getting? 0.0 for what? 1.0, recall 0.0. This is bad. Okay. If you go and look into scikit-learn, what recall is, you can actually get a much more deeper understanding of the same. I'll link it here. Okay. What else? Okay, guys, 5 minutes break. Okay, give me 5 minutes. I'll be back. Meanwhile, if you have any questions, you can type it down and I'll take those questions. Okay. Guys, 5 minutes break. I'll take questions for 5 minutes. I'll be back. Guys, no one has any questions. How to recall? Recall is a metric. I don't understand what question you are asking, because recall is a metric that indicates the proportional of actual positives. Okay, in here I have also written it. Okay, which were correctly classified. Okay, I have explained this actually in previous class as well. There's no, it's not a function or anything. So you guys are all able to understand everything that I'm teaching. That's why you're not asking me any questions. Am I audible, right, guys? Okay. I thought I'm not even audible. That's why you guys are not asking questions. Cool. Okay. Now, similar to classification, regression has its own sort of different sort of metrics that basically we measure on. Okay. One is R squared, okay, or coefficient of determination. What that does is it compares your model's prediction to the mean target values and can range from negative infinity, a very poor model, to 1. Okay. Area under receiver operating characteristics topic repeat, sir. Area and you want to you want me to repeat this ROC. Okay. See, it basically compares the rate of true positive and false positive, as you can see in this graph. Okay. This is the ideal case where like every value is true positive. This is an ideal scenario. This never usually happens. This will never usually happens. What this means is all your predictions are 100% correct, which is very unlikely. Okay. Ideally, you will get a graph something like this, which is good enough because it is leaning more towards true positive rate. That is what it is. I hope it's clear, Ramya. So here, what is Paret's function? Paret basically predicts it. We are making a prediction. Why are we creating this model? We are predicting because we want to predict something. Okay. For example, we want to predict if someone has a heart disease or not, which is our target column in the heart disease table, which is 0 and 1. So we want to predict if it is 0 or 1, and that is what predict does. And probability is like by what probability is this prediction correct or right or is being done. That's what proba predict is. Okay. Now let's go into regression. Okay. In classification, if we have precision, recall, F1 score, support, and so on and so forth. In regression, we have different metrics that we actually measure on. One is coefficient of determination, which compares your model predictions to the mean of the target values, and it can range from negative infinity to 1. Okay. Regression model evaluation metrics. Okay. Then we have mean absolute error. Okay. which is the average of absolute difference between predictions and actual values. And it gives you an idea of how wrong your predictions were. So lower is usually better. And finally, we have mean squared error, which is the average squared difference between predictions and actual values. Okay. Squaring the errors removes negative errors and it also amplifies outliers. Okay. Samples which basically have larger errors. And in here also, lower is better. Okay. Now, from what we know, we have seen this housing data frame a lot now. We are doing the same thing that we have been doing. Cool. Now, let's try to get R2 score. Okay. Once you have got trained regression model. Cool. Now, outside of the score function, R square can be calculated using scikit-learn's R2 score function as well. From metrics, we can get R2 square, and this is how we can get it. You see, we get R2 square from here, and in here, R2 square is what? 0.0. And a perfect model will get what? R2 square. A perfect model will get 1.0. Right? We are using y-test, y-test. That is perfect model. Y-test mean is basically imperfect model. Okay. Now, if you want to, if you want to maximize R square while minimizing MAE and MSE, then you get 1.0. Okay. Because we said lower is better. This is what we said for MAE and MSE. Okay. What is MAE? Mean absolute error. What is MSE? Oh, I wrote here MAE itself. It's mean squared error. Cool. Okay. Now, in scikit-learn, we can actually calculate mean absolute error using the metrics and so on and so forth. And we get MAE as 0.32. So basically, our model have an MAE of mean absolute error of 0.32. This means on average, our model predictions are 0.327 units away from the actual value. Okay. What does this means? This means on average, our model predictions are 0.327 values away. Let's try to get it in a data frame and see actual value prediction, so on and so forth, or whatever. Okay. For roughly 4,000 rows. Now you can see the predictions are slightly different than what the actual claim is. Right? Each of these predictions are slightly different than what the actual claim is. Okay. Now you can see, depending on what problem you are working on, having a difference like we do now might be okay. It completely depends on the problem that we are working on. And also depending on the problem, it also might not be okay. So it completely depends on what sort of problem we are working on. Okay. Let's see how we can visualize on graph. Okay. Now, if you see, blue are actual values and basically red is our prediction and how much overlapping we have. Okay. Similarly, we can also get mean squared error from metrics using scikit-learn. Again, we said lower is better, so 0.25 is okay. Okay. Usually, MSE is often higher than MAE because it squares the errors rather than only taking the absolute difference into account. Okay. Now, you might be thinking we have these three major metrics and what should we use? Okay. So R square is actually similar to accuracy in classification. Okay. It is very similar to accuracy in classification. MAE, mean absolute error, gives a better indication of how far off each of your model's predictions are on average. So you have X value and how far off the predicted value is. And and as for MSE, okay, because of how MSE is calculated, squaring the difference between predicted values and actual value, it amplifies larger difference. Let's say we are predicting the value of houses, which we are, pay more attention to MAE, okay? When being $10,000 off is twice as bad as being $5,000 off. Okay. And MSC, where $10,000 off is more than twice as bad as being $5,000 off. Okay. This you can understand when you start looking at all of these metrics much more closely. Okay. When you start looking at all of these much more closely. Okay. Scikit-learn has a very good documentation on scoring that you can actually refer. And I'll also link that. Okay. And you should read that if you want to understand it more. Okay. Now, what else? What else? What else? What else? Okay. Let's say so let's evaluate our model using a scoring parameter. Okay. We'll use the same heart disease data set and we'll try to evaluate it. Okay. And how we can evaluate the scoring parameter using basically cross-validation score. That is what we can do. This is something that we have been doing. We have already imported cross-val score and like basically it's the same thing that we have been doing. Divide into feature variable and so on and so forth. Let's try to get cross-validation score. Okay, we get cross-validation score. CV is 5, that's why we are getting 5 values, right? It splits that. If you want to get in percentage, we can basically do something like this, and then we are getting cross-validation score as a mean 82%, right? If we want to get scoring, basically, um, if okay, if we want to say pass in the third parameters, that is the scoring, and we want to set third parameters as accuracy, then we can set that, and we get 82.48%, which is again the default thing, right? If we want to set the scoring to precision, we can set it, and then we can see it, okay, which is 0.83. If we want to set scoring as recall, we can set it. Scoring here, you see, we are setting it recall. And then what do we get? We get somewhat 0.85, right? And then we can also get F1. All we need to do is like last one, we need to set it F1, and we get what? We get 0.84. Okay. Similarly, let's revisit our what? Regression model with the housing data set. We go here. Okay. Now again, let's do the cross-validation thing. Okay, because we want to get cross-validation score. And let's try to get R2 scoring method is now R2, which is R square, basically. And let's see what we get. Because the data set is large, it will take some time. Okay. Uh, let's wait. I think housing has 10,000 data sample. That's why it is taking time. Right. And we get 0.65, right? Same. If you want to get MAE, that say scoring, give me negative mean absolute error. Okay. For MAE. And now we get cross validation MA score will be somewhat negative, and you will ask why negative underscore, because scikit-learn documentation states that all scorer objects follow the convention that higher return values are better than lower return values. Okay, that is why. It is just coming from scikit-learn's documentation. That's all. And I will link that documentation in here, okay, so that you can refer to it. And we are getting minus 0.47. Okay. Now, same for MSC, then we can use negative MSC, and then we should be able to get MSC, right? Now, how do we use different evaluation metrics with scikit-learn? So, third way of evaluating scikit-learn function, um, we have sort of covered it already, okay? Because it is very similar to how scoring is done, but we have sort of already covered it. They all work by comparing an array of prediction called Y-breads and actual limits, okay? So for classification, it is usually accuracy score, precision score, recall score, and F1 score, okay? That's how we do it, but they have their own sort of functions that come from scikit-learn. If you see here from metrics, you can get accuracy score, precision score, recall score, F1 score, and so on and so forth. Okay. Third way for evaluation. Okay. We use again heart disease metric. We are using random forest classifier. That is why we have accuracy, precision, and so on and so forth. We use Y test and Y pred, and basically we are trying to get accuracy and precision recall F1 out of 8. Okay. Similarly, for regression method, same thing. It's just that we are using now R2 score, mean absolute error, mean squared error, and so on and so forth. And in here, if you see, doing the same thing, using a random regressor model, getting from matrix R2 square, mean absolute error, mean squared error, and then we are using it here and applying it on Y test and Y prediction. Okay, and we get 0.81 and 0.83. We have covered basically a lot of things now, right? What you need to keep in mind is you always need to evaluate your model. If you don't evaluate your model, then basically you will eventually have bad sort of implementation which you don't want. I link on scikit-learn's documentation that basically you can use and learn to dig deep on how you actually evaluate your model. Okay. Now, if you remember, I don't know if we have this diagram in the same notebook. Yes. If you remember, now we have covered our modeling. We have covered features, we have covered evaluation, we have covered data, we have covered problem definition. What the hell is left now? Experiment. Okay. Experiment, 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 make it reiterative, keep on experimenting, and then only we can reach to a proper solution. Okay. There is no short rule in machine learning because again, we are making some sort of prediction. That is why we need to experiment. So the first prediction that you make, okay, let me write it in large stuff. Okay. To experimentation. So the first prediction you make with a model are generally referred to as baseline predictions. Okay. First prediction that you make are generally referred as baseline prediction. It is similar to for the first evaluation metrics you get, and these are generally referred to as baseline metrics. The first initial metrics is also called as baseline metrics. Okay. What is your goal once you get baseline prediction and baseline metrics? Okay. Your goal is to improve on these baseline prediction and baseline metrics, and how you can do it, how you can do it, how you can do it, guys, how you can do it, how you can do it, how you can do it. Everyone's sleeping. How you can do it? Type, type, type. How much time it takes to type? Type. How to improve? Okay, we are not moving forward unless anyone types. Am I teaching some ghost or what, man? Are you guys even listening? Yeah, it's right, Siva, but why is it taking so long for you guys to reply? Why is it taking so long? Are you guys sleeping or what? How many people are there in this chat? 151. And in 151 chats, I get like 3 or 4 responses. That also one response after like 5 minutes. Everyone else is sleeping. Why are you not responding, guys? I literally said it 1 minute ago. You need to do experimentation and you can't even repeat that experimentation. So they basically turned on their Zoom and then went to movie. This is idiotic, man. Seriously, very bad. Super bad. At least you guys can repeat what I'm saying. I didn't even ask a question. It was just a repetition of what I was saying. Okay. So there are two main methods to improve baseline metrics. Okay. One is obviously from data. Another is from model. Okay. One is from data. Another is from model. These are the two ways you can actually improve your baseline metrics. Okay. From a data perspective, you need to ask certain questions. One, can we collect more data? In machine learning, ideally, more data means better results. So you need to ask, can we collect more data? Okay. The second question you need to ask is, can we improve our data? Maybe filling missing values, finding better encoding, or maybe some data points might be missing. You can add, broaden your data or something like that. You need to ask these questions. Okay. You need to ask these questions. From a model perspective, from a model perspective, you can ask, is there a better model we can use? Okay. You can ask, is there a better model we can use? We have already referred cheat sheet map above. Okay. Is there a better model we can use? Can we improve current model? Okay. Basically improving the hyperparameters and so on and so forth. Okay. Uh, you hyperparameters. Okay. These are the things that you need to ask. Cool. What are the hyperparameters? Answer that. What are different hyperparameters? What are hyperparameters? What is a hyperparameter? type. What is a hyperparameter? Arguments, okay. What else? Any other answer? Any other answer? Hyperparameters are the variables which determines the network structure. Yes. For example, for random forest classifier, this is how we can get hyperparameters, get params, okay? And we can see these are different sort of hyperparameters that it uses, okay? You can see max depth, mean sample split, and estimator. Each of these is a hyperparameter for random forest classifier, which you can adjust, okay? For example, if you are cooking, you can adjust cooking time and cooking temperature to get good food. For example, if let's just say if you increase the temperature a lot, then your food will be burned. If you cook it for too long, then it will be overcooked. If you cook it for too short, it will be undercooked. Okay. If you basically lower down the temperature, it will be undercooked. Okay. So similarly, we need to tune in these hyperparameters to actually get the best results out of it. Okay. Now, we'll try tuning some of these hyperparameters that we see above. Okay. And we will see what we can do. So we can tune in hyperparameters by hand. Okay. We have worked with different sort of data set and so on and so forth. What we can do is we can somewhat split the data in a way where like we can try to tune it. So let's try to do it. Okay. Let's try to do it. What we'll do? Let me whoever is asking topic today can go to hell. Okay. Let's try to do it by hand. Initially, we were doing 80-20 split. Now let's try to do 70-15-15 sort of split. Okay. And we'll try to tune in with hyperparameters on this 15% of sort of split. Okay. So let's create a function which will give us a value predictions. Okay. This is all we have already done. We are just repeating the same thing. We have just created a function so that we can reuse it. Okay. Again, I'm using the same thing that we have above. We have done this already. We are using random forest classifier. We have done all these scoring sort of thing. The only different thing is now we have a valid data set, validation data set, which is 15%. Okay. 15% validation we are saying, 15% test data we are saying. That is why we have X valid, X test, X valid, X test, and same here, right? 0.3, 0.5, and so on and so forth. Cool. Let's remove this. Okay. We get accuracy 80%, precision 0.78%. recall 0.88%, FN score 0.82%. Correct. We get all of this. We have seen this already. We have samples and so on and so forth. Now what we see, we have training data that has 212 samples. We have validation data that has 45 samples and 45 labels. And we have testing data that has 46 samples and 46 labels. Okay. Now let's try to improve it by tuning hyperparameter. Okay. Firstly, let's try to evaluate prediction. Okay. We made predictions and now we are evaluating these predictions. We get these scores. Okay. Now it looks like that our n estimators value performs worse than the default. Perhaps there's a better value for an estimator. So earlier when we were having this as 100, it was performing much better. Okay. It was performing much better than now. That means that we can change this. What are the hyperparameters that we can change? Now, this can actually take a while, but there is a better way to do it. Now, how can we do it? Hyperparameter tuning with randomized search CV. What this does is, okay, it allows us to randomly search across different hyperparameters to see which works the best. Okay. It also stores details about the ones which works best. Cool. So let's try to do this. Ideally, the description. Okay. This is the format that it comes in. Hyperparameter grade randomized search CV. This is the format this usually comes in. Okay. We initialize the dictionary with bunch of hyperparameters. Okay. Now, where did these values come from? Where are these values coming from? This is made up, right? We are not generating anything. We just made it up based on our understanding and so on and so forth. Okay. But this is also not completely pulled out of thin air, because we are getting these hyperparameters after reading scikit-learn's documentation. And hence again, it becomes essential that you read these documentations well. Okay. So it is coming from this documentation. Now we have got the parameter distribution dictionary set up. Okay, randomized search CV will look at it and it will pick up a random value for each, instantiate a model, and with those values, we will test each model. Okay. How many models will it test? As many as there are combinations. So as many combinations that it can make, it will test that. Okay. So it says it has 1,440 potential combinations for hyperparameters to test. That's a hell lot of combination. Okay. So what we can do, we can actually set up a parameter called as an iter. Okay. And that will limit the number of iterations that it will go through. Okay. The results that we'll get will definitely be cross-validated, because that is why it says randomized search CV. CV here stands for cross-validation. What does cross-validation means? Type. What does cross-validation means? Type. Type fast, guys. We don't have time. What does cross-validation means? What does cross-validation means? I mean here, I know to check, that is like simple English deduction. I mean in here, in what we are doing. Right. In two data set, but in different sort of data sets. Right. Correct. Validating by taking samples in sequence. Correct. Okay. So let's try to do it. We are basically doing the same thing, getting like splitting data and so on and so forth, using random forest classifier. And now we are using randomized search CV. We are saying do cross-validation for 5-fold. Okay. And then we will do param distribution. Basically, these are the param that we are doing. Okay. And we have set n iter. N iter is what? We are setting it to 30. So basically it will run only 30 times. And let's see what do we get. So it will check for 30 different combinations. Randomized search CV will check it for 30 different combinations. So it is saying total time taken for 30 random combinations of hyperparameters is 43.52 seconds. And do remember that it has also done cross-validation. Now let's see in this 30 different combination, what are the best parameters? And it says these are the best parameters, where n estimator is 200, min sample size is 6, min sample length is 4, max feature is log 2, max depth is whatever is 30. Okay. Now, what we can do? Make predictions with this best parameter. And let's see what we get. And we are getting somewhat 85% of accuracy, precision 85, recall 85, and so on. Right? Now, thanks to randomized search CV, what we have done is we have had bunch of hyperparameters and we got a nice boost in our evaluation metrics. What else can we use? We can actually do the tuning also using grid search CV. Okay, we can also do this with grid search CV. Okay. Now, the main difference between grid search CV and randomized search CV is that grid search CV searches across a grid of hyperparameters exhaustively, and it will try every combination possible. Whereas randomized search CV searches across a grid of hyperparameters randomly, stopping after n sort of iteration that we pass it. Okay. Let's see. This was our param distribution. Let me also write it. What is the main difference? Okay. So that you guys know what is the main difference. Okay. Okay. We have tried, in our case, our data, we are relatively using small samples. Okay. Usually it can take a lot of time to do grid search CV. Okay. Basically the formula is, okay, let me quickly write. I have written the difference here. Main difference grid search CV, randomized search CV is it searches across a grid of hyperparameter exhaustively, which means it searches across all of the parameters, while in randomized search CV, we provide it with number of iterations and it does it randomly. Okay. How many models it will look for? It will look for some sort of this formula, which is max features, min sample, so on and so forth, and it will calculate. You can look into it once we are like, when you read this notebook, you will understand where this 360 is coming from. Okay. So now we already have this param grid. So let's see. We already have this param grid. Cool. And now we have created grid of parameters that we want to get. So let's see what are we getting. So there are 24 combination of hyperparameters to test. Okay. And this is 60 times less than before, which was previous 1,440 parameters. So in grid, the formula is as such that it takes less number of combinations. Okay. You can refer to the documentation for exact calculation, how the grid is calculated. Okay. But the calculation I have already written you. So you should be able to understand it when you go through this node. Okay. We are importing grid CV, doing the same feature split, grid search CV. CV is what? Again, cross validation. We are using grid parameters and so on and so forth. And then we'll try to train it. Let's see. Waiting. Okay, I think it's done. So the total time taken was 55 point some 69 seconds. Okay. Now let's get the best parameters. Okay, we got some best parameters in here. Cool. Let's try to do this prediction based on the best parameters. This is what we are getting from here, GSCLF, right? And let's try to get it. Let's see, 88% accuracy, 91 recall, F1 score, right? Now this is much better, correct? We can see our accuracy and stuff. Let's try to create a data frame and then see and visualize it. Okay. This is what we are getting. Accuracy, precision, and everything. Baseline, random search, and then grade. And if you see with grid search, we are getting the highest number of accuracy. Okay. After trying many different combination of hyperparameters, we get slight improvement. We are basically in the right track. There are other techniques that you can use. Again, like try more advanced models, or you can actually uh, or you can actually okay, you can try more advanced models, or you can use get more data. Okay. Now, once you are done with this, you can basically use Pickle, save this model, done. Once you are done with saving this model, you can basically get this model in here. You can make predictions again using Pickle. Boom. It works the same, correct? Are we getting this, right? We can also save this model with joblib. I already told you this. If we want to save something large, we can use joblib, right? Save this like here as such. You can make predictions in here as such. And then you can do, oh, Cool. I think we have pretty much completed our scikit-learn. I'll only do a very base sort of revision in the next class. Okay. Now we have pretty much completed scikit-learn. And if you have any questions, you can ask me now. We have 5 minutes to ask questions. That is if you guys even attended this class. I don't know if you guys did. Because seems like most of you are only here for attendance. Topic name is Kalki. Say this what? Say what? Kalki. That's the topic name. If after 2 hours of class, you guys have to ask me a topic, it's hopeless. I don't care like what rating I'll get or whatever. But guys, whoever in this class is asking topic name, I'm really sad. I don't think so. You guys will even get some good job if you don't improve your attitude. Plus, I don't know what you think of real life opportunities, but for junior developers, it's very hard. It's very hard in the market right now, especially because I know 80% of you are just chat GPT developer who just copy paste. And if you will be one of those who are copy paste programmers, it's very hard for you to get a job. I hope you guys realize this sooner than later so that you guys pay attention to what you are getting and leveraging. I hope all of you are serious about what you are trying to learn. It can be anything that you are trying to learn, irrespective of the topic. But you have to be serious if you want to be an engineer and continue to be an engineer. If this is not the thing that you want to do, then it's completely fine to be inactive in this class or any class. Otherwise, you guys have to be serious on what you are doing. I shared this notebook today. I'll share this notebook today because this is basically end of scikit-learn, and hence I'll share this.